If you like this video, please give it a thumbs up and hit the subscribe button as well as the bell to be notified of future videos. Thank you.
Hello Internet, we are back. We've got Colonel Basson with us. A very clever man, very smart man. I must warn you, we're having a bit of trouble with our internet here. I'm convinced it's got something to do with Ukraine and Russia. Wonderful, electronic warfare capabilities. Switzerland decided they're going to sanction Russia, and so now we have internet problems. Whatever, we will try and see what we can do. Now we're back to you, Laurus. You can tell us what actually happened after you now qualified as a flight test engineer.
Morning, Chris. Thank you. Yeah. So yesterday, as I said, we stopped where I just gave a brief SDC. Today I want to talk more about some of the projects we did, just to give the viewers an idea of what we did there. But before we start, I just want to mention a few things about the organizational structure at Tfdc, because there were some departments that were unique to Tfdc that you did not find on other bases, obviously due to its nature of the business. The first one is the Flight Test Instrumentation, or FTI department. Now you'll see any flight test instrumentation in the aircraft is in the orange color, so you can see that identified clearly. And the flight test instrumentation goes about, there's sensors installed all at various locations or at applicable locations across the aircraft. And then on board it's got a recorder, so these parameters are recorded. So it can be a pressure, temperature, it can be a vibration, whatever that might be. And you can have like hundreds of these parameters, and each parameter is sampled at multiple times per second. So it's recorded. I've worked on cases where especially in vibration, where you've got like 48,000 times per second that parameter is recorded. So the data is very voluminous. It's a lot. Now at that time, I just need to mention a few names, because there was a Sergeant Major Morris van der Heever, a very, very knowledgeable guy. People like Sergeant Major Ralph Muskie, Hannes Feil, Flight Sergeants Hans Reinecke, Dani Robenheim and Ludie de Jager. And these guys were really very, very knowledgeable guys, because they would design, manufacture, install, calibrate, and maintain the flight test instrumentation. On board the aircraft, there can also be a transmitter, so the data is transmitted to a telemetry station, ground station, in real time. So obviously another department we had was the telemetry department. At that time we had 2 wagons, so we could deploy, if we wanted to go and do tests. And so the data is transmitted real time. The flight test engineer sits in the wagons, telemetry wagon, and they monitor the parameters. We had 2. One was, we called it wagons because they were like these containers, but inside it looked totally different with all the fancy equipment. So one of them was called Fynbos, obviously because Fynbos was in that area, and the other one was Louise. Now Louise was specially configured for flutter testing, which I will get more into later. Later years, the head of the section was a Lieutenant Colonel Gerard Skeiter, and he then had a project where we made a nice, part of the project was to establish a nice telemetry room, so it was actually very nice. So in the beginning days, there were people like Donnie Miller, Trevor Slater, and then later Fanny Stadler and Stephen. So as I said, the displays can vary. Some of them, we had like what you call strip charts. It didn't look like your heart, when you're going to do a heart ECG. So it had a paper roll that rolled onto another one, and then you had like a needle showing the parameter, how much it, the magnitude of that. And interesting enough, it wasn't ink. It's a very special paper. That needle, if you the line on the paper is actually it's hot, it's a thermal. So it's very special type of. There could be displays, like if you look in the cockpits, the display that the pilot sees, but that's on the ground station. We can have even real-time video link. So the there's videos on board the aircraft, and that's transmitted to the ground station. Then the other department we had unique to TFDC was a department. So these were the computer guys. They were civilians. Initially, it was Infoplan people, subsidiary of Armscor. And they did all our computer work. They were also the ones that after the flight would give us the data, so the data would be downloaded by the flight test instrumentation guy, given to the data analysis guy, and they would process it to give us, like the parameters versus time. There were initially guys like Andrew Berger, Stefan Otto, Stefan Skuman, Albert Root, later Johnny Prinsloo, Fani Loubse, and Daniel Seegmüller. So sometimes we would also, they not only did data, but they would give a service to the General Air Force. As an example, there was a department in the Air Force that monitored all the vibration levels of the helicopters and also of the propeller aircraft. The department head was John Hofmeyer, and so we worked with him to make a program for him to manage this data. So we gave services like that also to the broader Air Force. Very unique one, not general stuff. And we also, for example, one time we had to create the cruise performance data charts that would go into the flight manual for the pilot to use for the Dakota. So Daniel Seegmüller and myself sat down. I gave him the equation, and he would type in, he would program it, so we created. So we had a small, what they called R&D department. So they supported mostly the flight test instrumentation department. So if the flight test instrumentation wanted a specific circuit board, electronic circuit for as part of the flight test instrumentation, this department would design, build it, and to supply it to flight test instrumentation. They also did other instrumentation. Just to give you an example, we once we had to do takeoff performance testing on the Dakota. So we had a video, we had to measure the distances. Now there's two distances of concern, from brakes release to liftoff, and then from liftoff to 35 feet. So we had a camera installed next to the runway, and what they did, they designed a pod that measured the angle, a sensor that measured the angle of the camera's rotating pod, and then they also designed and made a display to give you the angle output. And it was actually fancy. They also had a button on the side. So when you wanted to read the data, the angle, you press this and it froze the screen for a while. So it gives you time to write down the data, and obviously the angle was calibrated with the distance on the runway. So they would do things like that. Also, another example in that same test, the most difficult part is to get the liftoff. You don't know where the liftoff, it's difficult. So what they did, they installed a light on in one of the windows of the Dakota facing the video camera, and on the undercarriage there's what they call weight on wheel switches. So when the aircraft lifts off, the switches open, they go off if you want to. So they made a circuit, so when that happened, the light flashes, so that's when it was liftoff, and the angle. So they made special equipment like that, also to support all the testing. We also had a photographic department, and it was not unique to TFDC, but because a lot of other bases. What was a bit unique there is install video cameras on the aircraft. To install a video looking at the bomb, so you can see when the bomb, video the bomb and its behavior as it drops. And those video cameras were maybe, the top size of my finger, like this. So the photographic department, they would work with the flight test instrumentation to to stream this down to the station, so because we're live streaming as you in real time to monitor the video in the telemetry wagon, for example. So we had functions like that. We also had a engineering office, and some of the flight test engineers, as I said, like myself, I also did mechanical engineering work there, especially supporting the installation of instrumentation to do the tests. We had a drawing office, where we created drawings for the installation of the instrumentation. And then we had people there like Sergeant Major Brits, Flight Sergeant Kratz, Vas Potgieter, and then Craig Oret, Neil Johnson, Jon van Eden before he became an officer, and Lermy Loupscher. Then we had our flight engineers on the helicopter side department, Pete Els, Andy Pentlebury, and the fitter was Ian Charles. We had instrumentation, the Sergeant Major Ari Erasmus, the electrical guys, Sergeant Major Martin Richards, and Philip Hutchings in the earlier days, guys like that, Frikkie de Beer. Now, and then we had the radio radar guys, like Sergeant Major Dou Willemse, Hein Groenewald in the earlier years. We had also a base workshop because they would do the mechanical work to install the instrumentation. What you will also see on a flight test aircraft, it looks like a long boom in front of the aircraft. So, and the purpose of that is, you'll see at the end of that, it's got a sensor to measure the pressures, the total and the or pitot pressure and the static pressure. And from that, we get airspeed and altitude. And then it's got those, it looks like a little vane. One is in like this, is for angle of attack, and one is like that for side slope. Design the boom, install it on the aircraft. So that manufacturing is done by the workshops and people like Sergeant Major Leon Janssen van Vuren, Flight Sergeant Nico Barnard, and earlier years John Prinsloo. And then, of course, we also had the armorers, of course, because a lot of our testing had to do with weapons testing. So guys like Sergeant Major Fred Els, Flight Sergeant Norman Williams, Ernest Maria, Rian Stein, Hans. So, and they did a lot of work, because but although these were the same functions you got at other bases, they were focused on evaluation. Like, for example, when there were new bombs that were tested, the first guy in the SAAF, the armorers to handle them, was Sergeant Major Fred Els and his team. And they would also do evaluations. They would write us, especially in the maintenance practice, because eventually those things must find its way into the aircraft maintenance manual, and their report would be part of our test report also, so very much focused on doing evaluation. So now, of course, each task that we did, and as I mentioned previously, in flight testing, we have to be very methodical. What we call the build-up approach, slowly increasing the envelope. You don't just go charging in their guns blazers, or like the Titanic's captain's last word, stuff the icebergs full steam ahead. Now, all our tasks started with a tasking from SOTF, Staff Officer Test Flight at Air Force Headquarters. And interesting, you're speaking about from Rhodesia. Actually, one of our SOTFs at one time was Commandant or Major Paddy Morgan. He was a navigator in the Rhodesian Air Force, and we had various throughout the years. But in any case, so once the tasking is given, a task leader is appointed, and it can be a flight test engineer or test pilot. It depends on the nature of the task. If it's more engineering related, it will be a task. It will be a flight test engineer. Or flying related, just flying, it will be a test pilot. Then the task leader sits down, analyzes the tasking to see what's the deliverables. He would generate the test plan, and in the test plan will be covered what all the test points that will be conducted, the conditions, you know, the airspeed, the altitude, the power setting, etc., that at which the test will be conducted. You would also define the flight test techniques. You would also define the parameters that needs to be recorded: airspeed, altitude, vibrations, loads. That obviously list will make its way to flight test instrumentation for them to design the system to record those parameters. Then also the risk mitigation was an important part, you know, identifying all the risk as well as the mitigation. And we had a saying, there's a saying, plan the test and fly the plan. You don't deviate. If you find something that's, you know, strange or not in order, you would stop the test, analyze before you continue. You know, there's been many cases of people that started going off the plan and then they end up in a crash or you know, even worst case getting killed. You know. The test plan then would be presented to what we call a technical and safety review board. That's usually other members in Tfdc and also the chief test pilot and the chief flight test engineer. Now, we provide services to both the industry and internal to the Air Force. So if there's obviously external projects, those guys will also attend the technical and safety review board. And there's two main focuses in that. The one is to see that the tests are complete. That's the technical part. And then there's the safety part. Are you doing your test safe? Or this, you know, if you take a simple example, if you're doing a test at minimum speed, have you got enough height above ground so that if you inadvertently stall, you've got enough time to recover? You know, so those type of things, they look at your build-up of your test. So then they would give approval to go and fly. And then there's also another important document, is what we call the certificate for flight trials, that you needed before you go and test, because that came from where I worked previously, that office at Air Logistics Command. So what this would do is it would confirm that all the necessary engineering has been done, like the drawings are in place, the necessary analysis has been done, the necessary qualification testing has been done, and it's safe to start the flight testing. So there's a whole sequence of event even before you start with a flight test. Then you would generate, from your test plan, you would generate a test cards for that specific sortie, that flight. You would brief it in very thoroughly in detail. These briefings can sometimes be very long, you know, because you need to look at all the safety aspect. What is a knock-off criteria, you know, and especially if there's a chase aircraft, so there's another aircraft flying to, you know, with this aircraft, there's a safety observation, you know, especially like if you do on a first flight, you would check there's no oil leaks and see if nothing of the panels or anything out of the ordinary has happened. So that would be briefed in detail. You know, how the chase aircraft, what we call pickup, you know, where must, you know, with a test aircraft, because the chase aircraft would first take off, come around, and then what we say pickup, you know, so the other aircraft. So the detail, you brief the details, you know, also the coordination, if you've got a telemetry monitoring in the ground station, how that, you know, the coordination between that, and I'll get into that more. A good example is the flutter testing. Then you would execute the test, come back, thoroughly debrief, and then you would compile what we call our flight dossier, test flight dossier. So in there you would put in your test cards where, you know, you recorded data during the test, your what we call mass and balance sheet, the weight and the CG of the aircraft at takeoff. The pilot would also write a PFR, a post-flight report, to capture his immediate impressions, because, you know, you can have a series of tests and then at the end you write your final report, and you might have done that test a month ago and sort of not clearly remember, you know, what that, so. And then your data, as the data analysis guy starts giving you data, so everything pertaining to that flight is in the flight dossier. And we had these files and files, they go into a file. And then you would do data analysis as the data comes off, and eventually the final completed, and then write the report. Now there's a sort of a rule of thumb that for every hour you spend test flying, you spend 7 hours of preparing and post-flight activity just for that flight. But I think sometimes that can be more, you know, than what is usually the case, because you spend a lot. And you know, there's a lot of coordination, because you must get the config, you must get the armorers, for example, to load the bombs. If you're doing bombs testing, you need fuel, you need ballast, you need to check with the flight test instrumentation, is everything ready to go? Are all the parameters and the sensors functional? You know, so there's a lot of coordination just to get in the air, you know. In any case, so next I'll run through some of the projects we had where I was involved, and mention others just to give an idea, because as I said, our tasks varied. It can be from a investigation to a simple small clearance of just to clear this envelope for it to be operational, to weapons testing, to ultimately what we call a first flight. So it's a new aircraft never flown before, and that's the ultimate one. So the first task I got when I arrived there was on the Impala Mark II that increased the all-up weight of the Impala Mark II. Now, at the same time, in parallel, there was also a same project running on the Mirage F1. Its all-up weight was also increased. So we did a lot of, I was the task leader for the Impala, and Pierre Fouchier, one of the guys that won course with me, he was the task leader for the Mirage F1. General Barker flew the Mirage F1. He was the test pilot for the F1, and George Miller was the test pilot for the Impala Mark II. So we focused mainly on the performance. Main emphasis of the program was performance and the flying qualities, how the aircraft handled due to this increased weight. So we started off by doing a lot of these tests at Tfdc at the coast. And then a major test campaign, of part of the test campaign for such a big modification and new aircraft, is what we call the hot and high performance testing. So you must go and do it at a location where it's very hot and as high as possible, because the air is less dense, so the engine generates less thrust, sort of the worst case condition. So we deployed to Uppington to go and do the tests there. And as you can imagine, it was a big, well, for our standards, a big deployment, because it was all the truck. There was a truck with spares and ground support equipment and the tools. So all of us drove up, and then the aircraft flew over when we were at Uppington. Now, interesting thing, Pierre, the other flight test engineer, and Sergeant Major Fred Els and myself, we drove up in the operations room, or ops, at a brand new Toyota Hilux double cab 4x4 bucky, brand new. So the three of us drove up in that bucky. And, you know, we were near Brandvlei, which is, we've been traveling hours when it was my turn to drive. And I'm sitting there, and it's obviously very bored. The other two are sleeping. And I look down at the gear, the lever, the knob on top where the gears are indicated. And it's got 1, 2, 3, 4, you know, the H form, and reverses to the right after. And I sit there and I think, this is very strange. It hasn't got a fifth gear, but this is a new bucky. It should have a fifth gear. So out of boredom, nothing to do, I tried, fifth gear, it goes into fifth gear. So shortly thereafter, we stopped and we changed over, and I think Pierre was driving, and I said, Pierre, use the fifth gear. No, man. I said, Pierre, he said, there isn't a fifth gear. Look there. I said, Pierre, trust me, there is the fifth gear. He said, yeah, jy wil my naam afmaak. You want to make a fool out of me. I said, try it. So it took me another 30 or 40 kilometers to convince him, and he tried, and so he was very relieved when it went in. So, you know, they say necessity is the mother of all invention, but I think sometimes also boredom is the mother of discovery. So, in any case, so we started with the testing. We were also supported by the Overberg test range. There were two guys there, Jan Lindeke and Errol Eisel. Because they got this high resolution, high frames per second cameras, which was installed next to the runway and calibrated to the distance, so they could give us the exact distance, the takeoff distance, you know, the ground roll and the air phase. And we had a temperature there of 38 degrees Celsius, and just a week earlier, it was 54 degrees at Ograbi's waterfall. So we had a very nice, for us for the testing, that was good. You know, it could have been maybe 40 would have been better, but 38 was good. We'll take that, you know. So we did a lot of the testing there, not just the takeoff and landing performance testing, but also all other testing, you know, that we did there, like client performance and stuff like that. Now, of course, we should have, there's a SA infantry SI base there. I think it was 7 or 8, I can't remember the number. So their mess was full, so we couldn't stay there. We had to stay in hotels. So every night we went to eat out, and there was a steakhouse, Matador. And if you ordered a kilogram of steak and you ate that and you ate another one and you finished it, you didn't have to pay for the second one. And on the wall was a board with the names of the people with the most steak per night, and the top guy was 2.5 kilograms steak in one night. So, but of course, I just want to mention for Pia and I, we were new members at the Tfdc. So this deployment, this test campaign was the ideal opportunity for us to integrate into the unit, because you know, you're away from base, there's a sort of a different atmosphere. So we really bonded very well with the people, you know, even to this day, all of us that's been there, whether you're officer or NCO or whoever, we always talk about, you know, our Uppington trip, you know. So we were very lucky in that we had that opportunity, because it set us up well, you know, in terms of interpersonal relationship and integrating into the unit. Because then another project that I was involved is the on the Dakota, and I'm glad to report to Colonel Tony Smith, it was the real DAC, the piston engine DAC. What they did, they modified this aircraft for, it was a technology demonstrator for the maritime role. So later they did have a maritime DAC on the TP. So this was the first one, mainly this was mainly structural modifications. Later on the turbo DAC, the systems I think came in. So I was involved with some of the stress analysis, and we were also tasked to go and do the flight testing. So Andy Dunn, the test pilot, and I, we went to TFDC to go and do the test. Now the project officer was a Major Horace Block, and he was on that Shackleton that did the emergency landing in the desert. If I understood correctly, he was the mission leader for that. In any case, so most of our testing for that one pertaining, you know, to was performance and flying qualities. But because as you step into one of the modifications was, if you stand in front of the door to climb on board the aircraft, just forward of the big door, there was a window. And you know, the window size was maybe this wide and about this deep. So what they did, they made the depth double that. So that it was and I've got a picture I'll send you. It's not that DAC we tested, but it shows you the size of the window. And then if you, inside there was a seat facing sideways. So in front of this new big window, but the window had a door. So you would pull the door out, it was locked, pull it out, and you slide it out of the way. So the idea is an observer would sit there if they're searching for, you know, survivors in the seas or in the sea, you would sit there and look out. And so we started doing the testing. I had the test cards and directing the test and recording the data as Andy, you know, was up in front flying with one of the squadron pilots. So initially I sat in front, there was a table to sit there, and then I saw this at the back, opened the door, and I sat there, and it was very quiet. You know, there was no wind going in there, so it was really ergonomically very nice. So I thought, well, the noise is the same as up there. In any case, you've got the headset. I'm going to sit here. So I had the most beautiful sight, and we were doing the test along the coast, you know, Clifton, up and down the run there. And I was sitting there having a look at the beautiful beaches and everything. It's one of the most beautiful views I've ever had in the flight testing. So that's an example of another one. In course, another project we had when I arrived on the books, when I arrived at TFDC, was a propeller paint scheme on the C-130 propellers. And apparently, if I remember correctly, there was a C-130 and I think it was a major from 3-2 battalion that the aircraft was on the ground with the engine running, and he walked into the prop and was killed. So then this paint scheme was developed to evaluate, there were 2 or 3 paint schemes to make it visible to people, to warn them when the engine is running not to walk in. So we evaluated, but those schemes didn't work that well because it had this flashing effect on the pilot, so it distracted them very much. So we sent, the evaluation was completed and it was sent away, and we didn't hear anything of that again later. So then we had another test, it is typical investigation. If I remember correctly, it was a C-130 flying on the border or somewhere in north, and it was flying low level, and it had the sudden uncommanded pitch up. So the aircraft came down to Tfdc, so we did a lot of tests to try to replicate, see if we can find the problem. The pilots were Major Spoffy and Major Rich Beaver, and the navigator was Captain Steph Milan, and I can't remember the flight engineer and the rest of the crew. But of course, these 2 guys, they I nearly want to say legends in the transport world, and these guys, it was fun. These guys were poking fun at each other, teasing each other, and like the 2 old grumpy men, but it was extremely entertaining, and they're very witty, So we enjoyed it a lot, So Andy Dunn was the test pilot, so we on board, and we've been doing testing for about an hour, and suddenly they say, one of the guys said, tea time, and Andy and I look at each other, what's happening? Yeah, we're busy with a flight test. So we were just off the coast over the sea, and so they put it on autopilot because we control the airspace, we being Tfdc, so there was not a lot of traffic. Put the switch the autopilot on, and we just, if you step out of the cockpit down, there's a small, like a kitchen where you can make coffee, and one of them was just observing the aircraft. And here we're standing in the middle of a flight test having tea break, and Andy and I looking at each other, and we say, man, this is the way to test. Unfortunately, that was the one and the only time we ever did test tea breaking during a test flight. Then, of course, we had another task, was when the Oryx helicopter replaced the Puma helicopter. There was, I think they called it an A-frame, and it would attach inside onto the structure and extend it in the cabin and extend it out of the doors, and then at the end the ropes were attached for the fast roping. And then in the middle also there was a big rope or cable, and at the bottom underneath the helicopter, down there was this contraption. It was a metal pipe about this size in diameter and a decent wall thickness, and it was vertically and attached to this big cable or rope cable coming down, and it was about 600 millimeters high. And then around it there were about 5 or so, half of a pipe which pivoted at the bottom, and it was upright, so you can fold it down. It was spring loaded, and this is for hot extraction. So the helicopter comes with this thing hanging underneath. In the special forces pulls down one of these half pipes, and they sit on it and huddle around this vertical pipe. I think they also had they clipped on. So this was a new design. So we had to test this and measure the in-flight loads to see whether the actual loads were within the limit loads. So we had strain gauges, or in Afrikaans rakstrokie, now to measure these loads. Now rakstrokie is like a fine copper filament wire, and it runs in a pattern, like a up and down. I'll give you a picture of that. And then it's supplied by a voltage, and the output voltage is measured. So this copper rakstrokie or strain gauge is attached to the structure. It's bonded to the structure. And because if a structure is under load of a component, it deforms, because under load, or so we measure that voltage is a function, the change in voltage, because the Afrikaans word is better rakstrokie because it's been pulled, it's gerak. So then it changes the voltage, which means it's under load. So you measure what we call the strain. From the voltages, we can determine the strain. And for any material, there's a fixed relationship between the strain and the stress. So we could measure what's the stress on there. this was transmitted in real time to the telemetry station and monitored to see if it's not exceeded. And then we had recce's that came there to do fast roping and this hot extraction. It's incredible to see these guys hanging underneath the helicopter flying away at 60 knots or something like that. So we did this test. The task leader or mission leader from their side was a sergeant major from one recce. I remember their names, but I don't know if I can mention that. But in any case, there was also a sergeant major from Palaborwa, 5 recce, with a few other guys, and then also a captain and some other guys from 4 recce. So they were there for 2 weeks. So we did the testing, because you had different air speeds and different test conditions that you had to test and check the loads. So all the time we're monitoring it in the telemetry wagon. So they over the weekend there was a beer festival at the mess at the swimming pool at the mess, and they still gave us a parachute show jump. But I just want to tell you, what a bunch of nice guys, man! It was incredible. So nice to work with these guys. Really, really nice guys, so we did the tests, and that was another project example. I remember, of course, there was a flight sergeant, but thin. I wonder if he was 75 kilogram. And I was looking at this guy and I thought, because you hear about the special forces operators, the heavy packs they carry because they deploy for long. And I was looking at this guy and I'm thinking, how does he carry this pack? And then when I was listening to Sergeant Major S.V. Fourie, and also in one of his, I saw a presentation of his book where he had the 80 kilogram pack. So I think this guy I don't even think he was 80 kilograms. So it's amazing, what, just to look at this guy and think and know that this guy carries this heavy pack. Incredible. But it was so nice. We really enjoyed it. And their sense of humor was really good. We had a good laugh with them. Now, of course, a lot of our tasks were what we called weapons clearances. And that can vary. Weapons can be bombs, it can be missiles, it can be guided bombs. We also had the odd drop tanks that we had to do the clearance for that, for what we call external stores. Now, all of any weapons clearance program had 3 major phases. The first one is carriage clearance, or what we call in Afrikaans draagklaring. So this is with the weapons on the aircraft. You would do the performance, because you had to determine the drag indexes, which eventually went into the flight manual for the operational pilots, and the impact on performance. Then we did flying qualities. You also did in-flight loads measurements. And then the major portion of that is what we call flutter, or the actual name is aeroelasticity testing. Now, aeroelasticity is, or flutter testing is, if you look at the wing, if this is the tip of the wing and it bends up and down, that's what we call bending. So, and then you had, or if that wing would hit a gust, or an air pocket, it would start vibrating. Or if the pilot does an abrupt input, it would start vibrating. Now, there's 2 responses you can get. The one is the oscillation dies out, or it damps out, or it diverges. So that aeroelasticity behavior we call flutter. And that is very dangerous, because the aircraft can break up in seconds. So your flutter testing is very critical, and especially on the Mirage F1, which had a relatively thin wing, it was very susceptible, more susceptible to flight testing, to flutter, sorry. So that divergent mode is what we call flutter, and we just spoke generally about flutter. And in fact, if I remember correctly, there was a Mirage F1 that was lost due to flutter in its developmental testing. So we would, before we started with the flutter flight testing, there's a whole sequence of events happening before that. There was a department, the aeronautical division at CSIR, the Council for Scientific and Industrial Research, or in Afrikaans WNR, Wetenskaplike Nywerheidsnavorsingsraad. the aerospace division was Aerotech, and within there they had what they call the flutter department. And now the head of that department was a Dr. Vermeulen, and true to South African nature, you must get a nickname. So he was called Dr. Flutter Vermeulen. So, and he had his brilliant engineers, Stefan Vivier, Eric Wegman, Donald McLaughlin, Lou van Zyl, Rob Urry. And what's interesting, after I left the Air Force, I worked at companies in North America and in Europe, and they provided flutter services to those one or two of the companies that I worked in. So I nearly want to say internationally renowned. But in any case, what they would do, they would start off, because any stores that you add, or a combination of stores, especially like on the F1, you had to change its dynamic behavior, the way it oscillates. So we must make sure it's flutter free, at every configuration. So it starts off by them doing analysis to identify what we call the modes. Now a mode can be, if you look at the wing, this is the wingtip, it can oscillate like that. So that's what they call a bending mode. Or if it twists like that, that's a torsional mode. And for each mode, and there's various modes, they define the frequency, its natural frequency, and then also the damping. So you always want positive damping. Then what they would do is a GVT, a ground vibration testing. I'll send you a photo. So what the aircraft is supported on hydraulic jacks, and they shake the aircraft on the ground, and they also vary the frequency. So it's quite a complex setup. And then all over the aircraft, they've got sensors to measure the vibration, which is the accelerometers. We call that accelerometers. So they would shake this aircraft, varying the air frequency, and extract from that the structural modes. Then they would, validating the initial analysis, and then do superimpose the aerodynamic model and come up with all the modes and the frequencies and damping for each mode. So that's what happened before we get to flight testing. Then we would sit down with them and plan and do the flight testing. What airspeed and altitude we start, how do we expand it, in terms of increasing airspeed and altitude, the order in which we do it, first airspeed, and then we go to different altitudes and different Mach numbers. So those are all, and the increments, because you do it incrementally. And then we would do the flight test themselves. Now the flight testing, we always had to monitor it. It's controlled from the telemetry room, because you have to monitor it. So if you get what we call telemetry break, you cannot see the data that's being transmitted, you cut off. And then on the aircraft, they had an excitation system, because now in the air, aircraft is also being shaken, and we had accelerometers there to measure the response. Now, earlier years, way back, they had what they call bonkers. It's an explosive, small explosive on the wing, and then it would give like an impact on the wing, and the wing starts vibrating. And maybe Sergeant Major S.V. Fourie, he was a demolition expert. He should have been a test pilot. He would have been. In any case, so then it would shake the aircraft. But as you can imagine, you can only do one test point per flight. So then the Mirage F1, the flight control system was modified so that the control surfaces can vibrate. And you can also change the frequency, and that would induce the shaking. And then when we get to the flight testing, so the flight test engineer would monitor the strip charts with the accelerometers output the accelerations. And so you start off, you give clearance to the pilot, the test pilot, to start the excitation. He'll be on condition on the airspeed and altitude. And then he would switch on the system, and it would shake the aircraft for a minute or more. And then he would switch it off. We would call standby for analysis, because the acceleration that you measure with the accelerometer, the vibration, in other words, is as a function of time. You have to convert that into what we call the frequency domain, to extract the frequencies and get the damping from that, to see, firstly, whether the prediction or the analysis is correct, and whether you've got positive damping. So that now in the earlier years, the data was recorded on magnetic tapes. So you first had to rewind the tape, extract the data. Now everything is digital. in any case, then we would, once it's confirmed the damping is good, the pilot would be cleared to the next test point. So you increase the speed. And then you say, okay, go switch on, shake it. Now, while the thing is being shaken, the flight test engineer must monitor the vibration. And the big thing is you don't want to see it go divergent. And because if it goes, you must immediately call stop to the test. The call was pan, pan, and then the pilot must reduce speed as quickly as possible. But you must be very careful, because sometimes you see when the vibration starts, or at point you get a little bit of increase of the magnitude of the vibration, so you don't want to have a false stop. Then the pilot would stop, after the excitation period, and then he would reduce the speed to the previous test point, because that one has been cleared now. We know that's safe. And so you would expand, do the whole flight envelope. So this is very tedious. It's a lot of work. I spend many hours in the telemetry wagon on flight testing, So in between the analysis point, you sometimes have good fun within the wagon. But in any case, so that is part of the carriage clearance, the draagklaring. And there's a video. I will give you a link, and people can go and look on YouTube, which shows you the vibration testing, of the aircraft vibrating in the air. And I think there's maybe also where it breaks off, because as I said, this is very dangerous. If there is indeed flutter, it's seconds, then the aircraft destroys. So it's very critical. Then the second phase we did is the release, and there's two phases in that we look at. The first one is if the bomb is released, it clears the aircraft properly. In some cases, and there's another video link I'll send you, where you can find the bomb, if it sort of starts flying again, and it hits the aircraft or the other bomb. So this is the first part. We want to see it releases clear of the aircraft in the immediate vicinity, and then the subsequent trajectory is also important. Obviously, at Tfdc, all our testing we did with weapons, it was inert weapons, not live weapons. So next to Tfdc, we had a bomb range. So if we tested bomb ranging, then and this is where overbook test range came in, because we worked extremely closely with them. Because the Aerodynamic and tracking radar, which they would track the trajectory of the bomb, so they could give us three-dimensional position, speed of the bomb. So then you want to see it lands on the target. Missile testing we also did. There was this one test we did, it was a very complex test setup. The Mirage F1 was in a race course circuit, and at higher altitude, the Oryx helicopter was hovering. It had a flare on board, and then it had to be at a certain position at a certain time relative to each other. Then they drop the flare, and then the missile is fired to see if it seeks the testing like that. Obviously, a test like that takes a lot of, from a safety point of view, a lot of planning and risk mitigation and safety to make sure there's no problems there. And then the last phase was the actual live firing. In that case, like bombs, they would go to Uppington, and that's where those tests were conducted. Now, of course, just something else of interest is before the tests were done, because a lot of it was done over the sea, they would send a week or so before the time a nav warning out to the fishing boats not to be in that area on that date in that time. But before the tests are actually conducted, we had an Albatross and later an Islander to take off, and the pilots would do what we call a range clearance. If there's boats, tell them please get out of the area. We're going to drop live fires, live bombs. So that was a big part of our function, was this weapons clearance. Okay, so the next project was the Boeing 707. It had an in-flight refueling system. So and it had a upgrade and modification. So we had to. I was involved in the testing, but we did this together with the company. So I went to the company in Israel to do the discussion for a week for planning. But I flew up with the Air Force as Boeing, so they took off we had to be 2 o'clock in the morning at Waterkloof, where they did the customs clearance. Then they flew down to Woodspruit to fill up fuel, and then we took off because Waterkloof was too high, for full fuel or the necessary fuel that they needed. So we flew all along up, did the planning for the week, and then they came down to do the testing in country a while later. So we were operating from the Boeing from 60 Squadron at Waterkloof, and the Cheetah was at Louis Trichardt, and General Barker was the test pilot, and flight test engineer was Jean Rousseau. And the day of the briefing, because already it's difficult to coordinate these tests because we had different locations. So it was, and the day of the test, the telephone lines were down. So there was these squawk boxes. So we had to do via squawk box. But in any case, we got it. One of the pilots was still on the Boeing, Major Walter Knacker, a very nice guy. And we rendezvoused with the Cheetah on the border with Zimbabwe. We were doing the test in that area. So obviously the testing went about the handling of the aircraft to couple the basket and also the functioning of the system. And we did a lot of, the guys in the Cheetah did a lot of coupling. I think we were something like 3 or 4 hours in the air. And of course, this is what we call high gain tracking task, to couple that the probe into the basket. So that day, definitely, they earned their money, their salaries over and over again. So I think we did it over 2 days, did the next day, and we were on the border with Zimbabwe, in the South African airspace, under Limpopo. And that day, so we finished the test. I drove to Johannesburg Airport, flew down to Cape Town, and then drove to Bredasdorp in 1 day. So I had the dubious honor of traveling from the most northern tip of Africa to the most southern tip of Africa. Okay. Bar 35 kilometers, but close enough for government work, So, so that was a project. And then another project, there was a project going on. I wasn't involved in the actual test flying because General Barker was flying on the Cheetah. He was doing clearances for these Mark 82 bombs, which had a parachute in a canister at the back. Now the canister, there was a pin that kept the canister attached, and then it had a wire running, and the other end of the wire was attached to the pylon, and the wire ran on top of the bomb. So, so that was the configuration, the Mark 81s. And then General Barker was doing a test over the sea when he had an uncommanded pitch up, and fortunately pitch up and a roll to the right. He jettisoned all the stores on board, and he recovered. We saw the hot video. He was close to the sea, but he was close to ejecting. He said he was very close to ejecting. So he, fortunately, good piloting skills and reaction. He saved the aircraft and came back and landed. So then one of the issues that they suspected was this wire that I mentioned, because the wire was running on top of the weapon, and it was exposed to airflow. So it was vibrating in the air, and so they suspected maybe this it pulled the pin out. So we were tasked, myself and another engineer, Kobe Lotta, they wanted to install one of the UTB's cameras, very expensive, camera on the station next to it, so that it can video the behavior of the wire, running on top, exposed to the airflow. So we did the design of this installation contraption. I did the stress analysis, and if you go near Bloemhof, and General Alexander will know what I'm talking about, there's a dam there. I think it's the Bloemhof dam wall, and this one face of this the side of this looked just like the Bloemhof dam wall, so we called it the Bloemhof dam wall, this installation. In any case, so they did the test. Now, very nervous because, if this thing falls off, it's a lot of money. It's not a good thing. So fortunately, it all went well. So that was just an example of, sort of the mechanical engineering stuff we were doing. Because then there was a project where the Air Force re-engined a Mirage F1 with a MiG-29 engine, the Klimov. I think it was called Klimov. So this was a very obviously top secret the early 90s project. We used to joke, we say this is so top secret that any documents you must sign with the eraser, and when you pray, you must pray under an alias. So, so top secret. In any case, the main contractor to modify the Mirage F1 was Aerosut in South Africa, aerospace company. I was just partially involved in that. In the beginning, I was called in because Colonel Jan Marais did what we call the baseline performance testing on the Mirage F1 before they did the modification, and I was called in to do the data analysis. And then I went up for a few meetings with the Russians where we discussed, the data analysis methods and things like that. And then now all the conversations with them is through a translator. So don't try and tell a joke through a translator; it doesn't work. Okay, so and then we had this meeting. It was a week-long design review, which each system, a guy responsible for his system would come and present the status, and we identify the any issues and what is preventing it from doing flight testing. And this this translator, his name was Sergey, because it's a very critical job. If he translates wrong either way, it can have grave consequences. So. Because if ever you saw a guy under pressure, was this guy. When we had a break, this guy was outside and he was smoking like 4 cigarettes in no time just to calm his nerves. I felt so sorry for him, but this guy also, he earned his salary over and over again. But in any case, there was this one old guy, Russian. He looked like Brezhnev, I called him Brezhnev, and he was sitting just like close to me. And he would listen to the other guys, and then he had this paper. He takes this paper out, just one page, folds it open. He's got his pencil, still the ones that you sharpened with his eraser, and then he would erase, write something, erase, fold up the paper, put it in his pocket. And a while later, listen to the guys, a while later, he would take it out, and so he went on. His turn to speak was only on the Thursday. We started on the Monday. So in any case, this guy, Thursday came now. This was the time of before computers, so we had an overhead projector. So you made a flimsy, just off this one page, and it was just a graph. And this was the thermodynamic cycle of the engine. And this guy started talking, Brezhnev. Of course, he spoke and he spoke. After 3 hours, I think about 3 hours, his own people say, the Russian guys, okay. Everything is good. Just stop. And it was incredible. Everything was here in his head. He just spoke from this one page. It was just amazing. I looked at this guy and thought, wow. In any case, then of course and I'm sorry, I'm going to disappoint Colonel Tony Smith here. I was involved on the project where the Dakota was converted to the turbo deck. So there was a company in the US called Basler, and they had what they call a STC. It's called a supplementary certificate to convert the DACs from the piston engine to the turboprop. Now, just a bit of background. If a company like Boeing, for example, develops an aircraft, new aircraft, they certify it, then they get what they call a type certificate. Now, suppose another company buys that aircraft, and a while later they decide they're going to upgrade the avionics. Then they go through a certification process, but they get what they call a supplementary type certificate because they're not the original equipment manufacturer. So the Air Force decided to convert these the Air Force Dakotas to the turboprops, and there was an agent. I say like an agent, the guy that brought the mods into South Africa. So the initial DACs, the project office was at Snake Valley, just next to SWAT, Air Force Base Swartkops. But the initial DACs were converted to at the hangars in Bonneboom Airport. And I think subsequently, eventually, there were also some work done at Eiserplaat at 2 Air Depot. So we were called in to do some testing because obviously it had to get clearance from CAA, the Civil Aviation Authority in South Africa. So we went to them to present our test plan and started testing. So we flew the DAC down to Tfdc. Now remember, all the developmental testing had been done. So we're just doing spot checks and just showing that it's good. Now, one of the tests we did is what you call the VMCG, V for speed, velocity, and minimum ground control speed. And what this speed is, if in the case of the deck, it's got two engines. So when it takes off and one engine fails, when it fails, the aircraft is obviously going to deviate from the runway center line. The pilot is going to notice this, react, and bring it back to the center line. So there's a regulation. The VMCG is the speed defined where that deviation from the center line is within 30 feet. And it's a certification regulation. So this is one of the tests we did. So we had a bucky behind the deck on the center line, chasing the deck, and I was standing on the back with a camera mounted on top of a video camera. And I just want to say, if you stand next to a runway and you see a deck take off, it looks very slow, but chase it with a bucky and you realize how fast the deck is. so we did that test, and we did a lot of other testing also. And another one that may be of interest was what we call the flutter demonstration test. So we had to go 15% beyond the maximum speed to, like a safety margin. And so I was flying with Dave Stock, was a test pilot flying in the Impala Mark 1, and I was in the back. So we were doing chase for the aircraft. And it's incredible if you're flying behind an aircraft like that, you see the movement like the rudder and the elevator. So it was Dave's eyes went like this when he saw it. Yeah. Because then another project that I want, more larger project, was there was a project Baviaan, and Baviaan was about replacing the Harvard trainer aircraft. Now there was some initial activities which I was not involved, so the project team went to look at different aircraft, and they went to Brazil. The company there is Embraer, and they had a Tucano trainer aircraft. They went to Pilatus in Switzerland to look at the PC-7 and the PC-9. They went to Poland. They had a aircraft called Orlik, so they looked at that one. I think they also went to in Ireland, looked at the Shorts Tucano. And there was an aircraft also, a trainer aircraft in France, the Omega. I think they went to look. As I said, I wasn't sure. I wasn't involved, so I don't know exactly the details what happened there. But what apparently happened was Pilatus was the preferred supplier, but the Pilatus at that time only had the PC-7 and the PC-9. The PC-7 had a 700 shaft horsepower, but it didn't have an ejection seat. While the PC-9 had a ejection seat, but it was a 900 shaft horsepower, which was very powerful. The Tucano had the ejection seat and a 700 shaft horsepower engine, so that was the right one. And as outsiders, we thought, this is the candidate. It's going to happen. This is the one. And all the rumors we heard was Tucano is the aircraft. And then I nearly want to say, out of the blue, George Miller, test pilot, and myself were tasked to go and evaluate the PC-7 Mark II. So apparently what happened in the meantime, Pilatus, realizing they don't have the exact aircraft that the Air Force wanted, they took the PC-9M modular aircraft, the airframe, and they installed the 700, well, actually it's 750 shaft horsepower, flat rated to 700 shaft horsepower. And this aircraft came up. It was still a prototype. So George and I were tasked to go and evaluate this. Now there was what they call a URS, a user requirement specification from the Air Force, defining what is the requirements of the Air Force. So we went and evaluated against that requirement. As it turned out, there were two aircraft, prototypes. The one was a registration number Hotel Mike Romeo, HMR, and the other one was Hotel Mike Sierra, which is HMS. The difference was the HMR, the horizontal stabilizer at the back where the elevator is mounted on, the horizontal stabilizer was horizontal. But the other one was down, sloped down, or as we call it, anhedral. So we went to evaluate these two aircraft, went to Switzerland and gave our report, and the Air Force decided to take HMR, the horizontal stabilizer that was horizontal. There weren't major differences, significant, appreciable differences. There was a little bit of better lateral directional stability on the one with the anhedral. But now this was a prototype, so and Pilatus, although it's a military aircraft, they had to get certification from FOCA, the Federal Office of Civil Aviation, to get an export license apparently. So, but in any case, they had to do all the development testing. So at times we would go back there, if they done some testing, and we were going to do some check testing. One of the cases, interesting, when we arrived there, and I asked them, you must show us an in-flight to a demonstration of the lowering of the landing gear with the emergency system. Obviously, we did all the necessary ground tests and risk mitigation and everything. You can expect they were a bit resistant, but after discussion, they said, no, fine, we can do it. So George flew with the Pilatus test pilot in the PC-7 Mark II, the test aircraft. And then there was another Swiss pilot flying the PC-9, and I was in the back taking video, as a chase aircraft. And later I spoke to some of the guys there. They said actually when they went to FOCA for certification, they used this video as certification evidence. So both of us benefited from that. The project also established an office there. There were some project members, an Arms Corps program manager, and there were two Air Force members, Lieutenant Colonel or Commandant at that time, Johan Loupsche, and Sergeant Major Olivier, and he was also on the Oryx project. In any case, so we went there a few times, George and I, to do evaluations, and Ollie gave us a tape with Afrikaans music, and on one of the tapes, one of the songs was on the tune of Pretty Belinda. There was a group, Touch of Class. The song was called Ek en my meisie, and the words were Ek en my meisie woon in 'n huisie, and Ek en my pa, ons bly by my ma, so this thing. And because it was so catchy, George and I was listening, when we're driving, we're listening to this. And then we would sit in the meeting and George would start with the tune. And then we burst out laughing in a meeting, we had to keep ourselves, and then it's stuck in your head and you sit there, so. But was the one visit, what we would do, usually it was typically 2-week trips, and then we would fly back on a Saturday. And so we usually would go to the airport at 11 o'clock on a Saturday, book in, and then go walk around in Zurich until we catch the flight that evening. On the one trip, so obviously we got flying kit with us, not just your normal baggage, flying kit, and we had a lot of meetings and design reviews, so we had a stack of documents. So George and I arrive at the check-in, we check in, and the lady there tells us, oh, you're overweight, but no problem still. We said, oh, so what must happen? I said, no, you must pay for overweight. We said, what? We said, how much? Still no problem. She said 2,700 francs. That was a lot of money still today. And our eyes went like this. We said, oh, no, okay. So we went to the corner of the building, packed our hand luggage as much as we could, and got our suitcases to the limit, checked it in, but then we still had other stuff. So the other guys, when they arrived, they could take it for us, because it's books and things like that. But then, very interesting. So we walking to the gate, and there's one place in Zurich airport, there's like a big passage, very wide. It's nearly like a wall, and there's seats on the side. And we're walking along, and at the corner of my eye, not taking notice, there's a guy reading a newspaper. He's got it up like this. And as we're walking along, he drops the paper to turn the page. And who is this? General Barker. So if he didn't drop the newspaper, we wouldn't have seen him. So he was on his way to Russia because he was working on that program with the re-engineering of the Russia. And him and the other test pilot was Rick Kalpen that I spoke about yesterday. They were the two test pilots for that program, the Mirage F1 with the MiG-29 engine. If I remember correctly, Rick Kalpen also did the first flight on that aircraft, with a modified aircraft. So total coincidence. Of course, but the project decided not to take the avionics that pilots usually have in the aircraft. And I think it was also they have this what they call offsets, you know, in the contracts and things like that. So it was decided to use the avionics system from ATE, Advanced Technologies and Engineering in Midrand. So that the aircraft was not called PC-7 Mark II, it was called Pilatus Astra. And I remember they telling us you must say Pilatus Astra because there was another aircraft, I think in Israel, called Astra. So you mustn't, you know, violate the, whatever you call this, the, then so we spend a lot of time at AT&E, you know, for design reviews. And at one point we had a mock-up, what we call a mock-up. So it's the actual cockpits with a seat, and the system's functioning. So we did a human factors evaluation of, was just to give the viewers an idea, we had our, what we call our test cards with these big A3 sheets. No, sorry, A2 sheets, yeah. And then we had a column with all, you know, like all the switches, the displays that we evaluate, and for each one across was aspects like the reachability, the tactile feedback, the legibility, you know, those type of things. So each block represented a test point. And, you know, after which we counted, we had something like 7,200 test points that we evaluated. And interesting, as part of this evaluation, we had to get a very tall pilot and a very short pilot, you know, because you have to check all the percentiles. And we got there was a helicopter pilot, and Air Force people know him. And I think somebody also mentioned his name in one of the program, Major Hojan Kronier. You're a very big guy. And the small guy was, I think his name was Mark Hills. So we got them to do that evaluation. So that project went on. Then eventually the aircraft was shipped to South Africa, to Eysterplaat at 2 Air Depot, and there they were assembled. So when an aircraft is assembled, after that you do what we call a post-production flight testing. It's maybe a flight or two. So, and there's a procedure that's generated, and you follow that. So George and I did the first few aircraft, firstly to validate the procedure, that everything is good, it's logical, you know, we don't miss anything or repeat unnecessary stuff. And then, as I mentioned yesterday, the operational test pilots from Langebaan, they started taking over from us, and I think we did maybe the first 5 and they did all the rest. There were a total of 60 aircraft. The first guy, pilot that got involved was a Major Dion Olshausen, was an instructor at Langebaanweg and also a helicopter pilot. Of course, then there was a project called Project Ovid. Now, the Aerotech was involved since the mid-60s, I think, with supporting and design of composite structures. So over the years, they gained knowledge, and so they decided to consolidate this knowledge by designing an aircraft, a composites aircraft. Apparently, Atlas Aircraft Corporation also had the same idea at the time, so they formed a collaboration with Atlas being the main contractor. And it was in the time when the Harvard was coming up for replacement, so they decided to design and build a trainer aircraft. So the aerodynamic design started in the end of 1985. And the aircraft was built, so it's all composites, and you'll see the structure, if it's not painted, is like black, because it was carbon composite structure. We called it the Tupperware aircraft. In any case, so TFDC was tasked to doing the test flying. Lyle Dodds was appointed as the project test pilot, and I was as the flight test engineer. So initially, Hans Reinecke was in the flight test instrumentation department. We spent about a month or so up at CSIR. Hans was installing, you know, because while the aircraft is still open, it's easier to install the wiring and the sensors. You know, once it's closed, some of the locations is difficult. I started writing the test plan, and we were doing some functional ground tests and things like that. In the time that we were there, they had a function where they unveiled the aircraft, you know, a big tour. And then we had also had in the time with a week-long design review, and General Wesley was very instrumental in that. You know, we went through each system to see what's the status, are there any issues, what must be done before we can get into test flying. And then the aircraft was, in that time also they did the GVT, the ground vibration testing, you know, of the aircraft. Then the aircraft was assembled to be able to fit in the C-130. And then it was flown down in the C-130 to Tfdc, and if Tfdc, it was assembled again. Now the head of the chief engineer on CSIR side was Dr. Robert Speth, very German, strong German accents. You know, he remember one day he got upset with this guy. He said, "These chappies, they can't fix them. They cannot even speak decent English." But excellent guy. Wow. Very good guy. And very knowledgeable. In any case, so the aircraft came to TFDC, it was assembled again, and then we started with all the preparing it for the first flight, you know. Now remember, this is a brand new aircraft. There's no documentation, no maintenance documentation, no flight manuals. So our crew got into you know, setting up all the maintenance stuff. And of course, if ever there was, on all the other projects I work, the professionalism from these people, it was really excellent. And this is where I saw this guys kicking, and it was just incredible. You know, how these guys, you know, well, I think maybe I've mentioned it, but what's that saying? No, sooner said than done. So acts a man of worth. And this is everybody they just did it. There was the proactiveness, the initiatives was really incredible. You know, all of the guys. And maybe I've mentioned it, I can't remember, but I remember it was during this time because, you know, there was a lot of, the respect was more based, the primary criteria for respect was professionalism. You know, we did respect rank and all that, but because we're a technical organization, so, and it was just incredible working with these people. So Lyle, and apart from drafting the test plan and everything, Lyle and I also had to generate like the procedures, the pilot procedure, you know, startup procedures and things like that, and the flight manual, those type of things. So I can't remember I mentioned, but this is one day I just like I said, we had good, you know, good spirit there. We could joke with each other, you know, but in a respectful way. And this is the case. One day we were at the aircraft, and Larmy Loubser, one of the fitters, I was teasing him, and he said, "Kaptein, my Tyson box, my ek bliksem." You know, I guess in English it's something like, "Captain, my Tyson boxes, but I destroy." You know, but you know, good spirit. It was really nice. In any case, we got instruction that we had to do the first flight by the 1st of May 1991, because the Pilatus brought the aircraft, the 7 and the 9, to South Africa. So they wanted to make a press release before the Pilatus aircraft arrived. So we were working our butts off. You know, obviously we drafted the test plan, and then we had to present it to this technical and safety review board. We worked throughout the night, no sleep. 5 o'clock that morning before the safety review board, we were still rehearsing and practicing and checking everything is good. So we got clearance, and then we started doing ground tests. So obviously all the time we have got data being transmitted real time. Mike Bartlett was flight test engineer monitoring, you know, the parameters with all the other engineers. And then started off with low speed taxi tests, you know. So Lyle just taxied on the hard stand, just to get a feel of the aircraft. Many times I think if the Martians or somebody was spying on us, I think these guys are crazy. They just go in circles like this. In any case, so then, you know, and build up, and then out onto the taxiway, which is first low speed taxi test, and then we got to the high speed taxi test. For that we also had the Oryx as a chase, and you'll see the photos. I'll send you photos. We had tufts all over the aircraft to visualize the flow, you know, over the different parts of the aircraft. So we had an Oryx as Chase with a camera, video camera videoing this. So on the high-speed taxi test, we line up and accelerate, say, to 40 knots, and then come back, then we increase the speed gradually all the time. Lyle will just give very, very small inputs just to get the feel if the response is smooth. Also determine at what speed the different controls become effective. And we build up the speed in increments until the aircraft flew off by itself. And you just kept like a foot above the ground, and then let it settle back. So then we went for the first flight. That was on the 29th of April, 1991. Again, the Oryx Chase, if I remember correctly, Andy Crawford was the helicopter pilot flying it, but Colonel Duncan Cook, who was the officer commanding, he was in the other seat as Chase aircraft. So also, if there's any issues in the air, he can support us, with, and then apart from all the engineers in the telemetry room, Bob Masson was also there with the checklist. So if necessary, he could support from a piloting point of view, so we had all these mitigating measures. So we took off, first flight ever. We did about a few functional checks, but because the main purpose of a first flight is to get the aircraft safely back on the ground, even if you've flown for 2 minutes, first flight. And before we came into land, Lyle first did at altitude, simulated approach and landing, and then we landed. So that was a big milestone, the first flight completed. Now, of course, the press release only happened in August. So this is a classical example of hurry up and wait. and a first flight for any flight test person is like the pinnacle of his career. So I was very thankful and blessed to have had the opportunity to incredible experience, a learning experience, So in any case, the aircraft was down for a while because there were some small snags we had to sort out. The major one was the landing gear doors. When they closed, the composite doors, the pressure field around it, it didn't close. There was a little gap on the one corner, so they were stiffened up and some other small things. And then we got stuck into the test campaign. First, we did the flutter clearance, so that we got an envelope to working, and then we did all the other testing, pitot-static calibration, performance. Now, all the while, every time we do this, we're monitoring all, like the loads and vibrations, everything throughout the flight. Obviously, flutter, you do that dedicated. So we did all the performance testing. We did about 100 hours of flight testing. And the next step, we were just about to start with the spin testing when the powers that be decided that the aircraft must go to Atlas and they must continue with the flight testing. So it went up to Atlas. It was then repainted and the name changed to ACE, ACE, All Composite Exhibit. And I believe they also took it to a few air shows to do the marketing. And then, unfortunately, during one of the flight tests, the reports we got was they had flutter on the elevator and it broke the control rod. So in the aircraft, Bob was flying, Bob Masson, and then Johan Vechter was the flight test engineer. They came back on their trimmers and above the runway, they ran out of control authority and the aircraft crashed into the runway. They survived. They were injured, but they survived, which is sort of testimony to the structures. And that was the end of it, unfortunately. But I'm sad to say there was a lot of negativity towards the projects in the acquisition world and both, and other areas. So I don't know why, because we talk about proudly South Africans and that. So, and at that time at the crash, they had the new molds already made, and when the aircraft left Tfdc, we had the three main problems, if I can call it that, not even problems, was the control forces in the roll was fairly high, but we had resident aerodynamicists during the campaign, Johan Barnard, the buddies from Atlas Aircraft Corporation, and John Monk, and we worked to solve that. So that modification just had to be implemented in the new design. The aircraft didn't have a park brake, and we had, if you look at the profile from the side, on top of the nose, where it joins the window, it had a sharp corner. So with the new one, they just wanted to make it more smooth. So those were the major problem. Now, the aircraft itself, as I said, was composite. But there was a lot of use of systems, existing system like the Arrowhead fuel pump was used. The Chieftain, which is a commercial, civil certified aircraft, the undercarriage was used. We had the Kudu, which was out of service. The avionics was used in there for the initial prototype. We had a Pratt & Whitney engine. Of course, it was incredible. You know, there was a crop sprayer somewhere in South Africa who got this engine via a company in Zimbabwe, and the propeller also. But what was incredible, despite the type of information we could get, like the engine, we got the engine model which we need for our analysis. The propeller, we got all what we call the prop efficiency chart, which was all available. It was really incredible, the information we could get. Now, we were told up to that time of the development of the aircraft flying that aircraft cost less than $2 million. So it was 1.6 million. And just to give you an idea, apparently the Pilatus aircraft, the PC-7, went for like $4 to $6 million, just to give you a comparative. So it was very sad, but I think in any case, I think even if the aircraft, the accident not happened, it was politically dead, you know, for some other reason, very negative towards that, towards the aircraft. So it was very sad from that point of view, but the project technically was an amazing achievement, you know, something to be really proud of. So of course, that was the, just to give us something interesting I just need to mention also was, we get this call, we're working long hours. We get this call from a Dr. Gyra Goridis. We just called him Dr. Gyroscope. He's from University of Cape Town. Now, you get what they call non-destructive testing. So, so on metal airframes, non-destructive testing includes things like dye penetrant and ultrasonic to pick up cracks that's not, you cannot see with the eye or you know, below the surface. And composites being new, because at that time, the only aircraft, full composite one, I think, was a Starship in Germany. So, and we had an expert coming out to give us, we had like a seminar on composite. And he said, because that was the early days of composite, he said, at that time, if you designed an aircraft and you're flying now composite aircraft today, tomorrow you're the leader in the world on composites. You know, so that was really good. But in any case, this Dr. Gyroscope, he asked us, he had a PhD student that was developing a non-destructive testing method for composites. So he calls us and he asks, can he just have half an hour, because this guy had a contraption, you know, it was still a prototype. If they can just have half an hour Friday afternoon after work, come and test this thing. We said, sure. So first thing, he arrives at 7 o'clock, not at after work. And this contraption of his had a laser based, and it had mirrors reflecting the laser. So with the transportation, the mirrors and with the vibration, the mirrors was out of alignment. So they first had to line this. Then they didn't work, and they had a problem because they were moist on the mirrors, you know. So 10 o'clock at night, they got this thing working. And we so tired, we sitting there. And then what they would do is they would take a hairdryer and just heat up the composites a bit, and then take a shot with a holograph, and you can see delaminations, if there are any, you know, because the two, if you got two, the fibers, if they delaminate, they're not attached to each other. And then this guy got carried away. Just one more shot, just one more shot, just one more shot. Of course, we got home the next morning, Saturday morning, 5 o'clock. we got home. And then when it was still at Tfdc, the one time we had to take the aircraft up to Snake Valley for major service. So the deck flew as support aircraft. Now, at that time, you're not allowed to fly in lightning, because if lightning strike the aircraft, it just go poof, basically, because it could not, it's not like a metal structure. In composite aircraft, the ones flying, they've got like a mesh in between the composite to absorb the current, you know, of the lightning. So we were flying up and we're going to Snake Valley, And when we got to Pretoria, it was thunder season. We had to divert. I think we ended up near the Botswana border just to avoid all the thunderstorms. And eventually we came in from the north. So it spent a month there for some, the major servicing. So that was that project. Now, of course, we worked hard, but there were many interesting and funny events that happened at Tfdc. So one day we get a call at Stellenbosch University. There was the Bureau for Mechanical Engineering, or Bureau for Mechanische Ingenieurs, is a BME. So they were given funds to do research to develop a afterburner for the Impala Mark II Viper engine. And this is research funds. And so they called us and said, do you want to come? They had it working, but it was just the afterburner just ran for a few seconds. So they said, do we want to come and have a look at the demonstration? So we said, sure. So a bunch of us Friday took one of these mini buses and went to Stellenbosch, about a 2-hour drive. Now this thing made a terrible noise, and it was just for a few seconds. And the one guy was telling us he was at the petrol station, and one of the petrol jockeys was saying, man, to the other guy, there's UFOs here, because you hear this thing, because it was close to where BMI was, but you don't see it. Just so of course, in any case, we watched the demonstration, but it also gave you there's a lot of research going on, and projects like that. And in any case, so at the time there was a Voedsel and Wijnfeest, so I guess food and wine festival at Stellenbosch. So afterwards, guys wanted to go there, so we go there, and obviously some of the guys enjoyed them, and then eventually we got away there, and then they said, no, we must go to the Dros. Now the Dros is one of the kuierplekke for the students, the place where the students visit. Now we're sitting there, it's already like 6 o'clock in the evening, another 2 drive in the afternoons. We must drive back. I say, Lyle, it's my wife and my wedding anniversary. I need to get home. And he said, guys, come on. Donate some money. Let him buy his wife some flowers, So the guys just give me money. So eventually we got home, I think 10 o'clock that time, because after we left, one of the flight test engineers that was on the course ahead of us, Gerard Jordan, he was then working at Houtech on the satellite program, and he lived in Somerset West. So they first wanted to go to him, another pit stop. Fortunately, nobody knew where he lived or didn't know his address. So we got home 11 o'clock. So the next day I went and bought my wife flowers, but I didn't look at the money. Of course, it was like the money they gave me was for a garden of flowers. It's the most I've ever bought my wife. And then, of course, we used to give every year, present a course for 4 weeks. It's called the Operational Test and Evaluation course. So pilots from the squadron and technical officers and engineers would come and do the course, and we would teach them about testing, because the guys at the squadron were like, some of the tasks we would also give to them. And so they came and did the test. And then what we usually do in the first week or so, they get a very simple task, usually to evaluate the human factors of an instrument, and just to get them into the mode of writing report and everything. So there's one guy, student, he gets the task to evaluate the attitude indicator on the Alouette. So the attitude indicator is like a line which shows the pilot the pitch variation and also the roll. Now, when the power switch off this line, because it's gyro-based, the gyroscope, and it's hanging like this, so what you call the gyro is toppled. Then when you switch on the power, the gyro starts to what they call erect. So the line goes to the horizontal, and then there's a knob on the side that you pull. So this guy wrote in his report just like this. This was his exact words. Upon pulling the knob, erection was achieved within whatever the 3 seconds, whatever it was. And this became a famous, they actually engraved it on a plaque, and they gave it to us as a gift when they left to remember them. And of course, an interesting incident we had was, and I think Jacques de Toey maybe also mentioned this, was there was a deck in the Air Force that was, they called it the photo deck for taking aerial photos. And so at one time they upgraded the system to a GPS-based system, and it came to Tfdc to do the testing there. Now, a colleague of mine, Peter Chaplin, he was the task leader. So they would do runs up and down, you know, and part of us over land and part of overseas and everything. And then they sent it up for development. And one day you walk in with this photo and there's a shot over the sea with a periscope. So the information we got was they went to the Navy, whoever they are, and they asked them, have you got any submarines at sea at that time? They said, no, none. They were, you know, or any submarines in the area. Said, well, we don't even have at that time at sea. So it turned out to be some other countries one. The news we got was, there were two countries, say country A and B, and they were not that friendly towards each other. And country B was testing some other weapons or something at the test range. So one of the hypotheses were maybe this was country A, or maybe somebody else's country, but it was totally coincidental. Because another interesting, actually funny incident, one day we, on the public address system, they say, everybody from, say, 11 o'clock must stay in their office and you're not allowed to look out of the window. So obviously people are going to look out the window. And what's happening was they were doing a test launch of the satellite motor at OTP. So everybody is against the window and you just see this big plume as they launch into the air. Of course, we had a Sergeant Major Chris Pretorius, and he was an aircraft electrician, but he was very gifted. So when any incident happened on the base, he would make a cartoon, and he was spot on, you know, and a lot of humor, you know, really good. Now, in the beginning times, the road from the Bredasdorp Barneskrans main road to Tfdc was a gravel road. It wasn't tarred. So then they tarred it, and when they finished, you know, there's these loose stones. So they said, okay, we can start driving, because while they were tarring it, we had to go all the way through the test range to Barneskrans and then back. So they opened the road, say, you know, drive on the road, but slow, you know, so that, you know, you can clear the stones off the road. Now, when you get to the junction, the main road, Bredasdorp Barneskrans, if you go over the road, there was a cattle grid with two concrete blocks with the pillars, and then a normal usual gate next to it. And along the left-hand side was the fence. So one morning we arrived there, and there's this car wrapped up. It gone through one of these, it hit one of these posts of the grid, wrapped up in the fence. So Chris drew a cartoon. Now the guy that had the accident had his judo colors, Springbok colors in judo. So you see in the cartoon this guy standing, you know, much taller than the car, leaning over the car with accentuating the Springbok badge, and the wording is, "You don't go left, you don't go right, you just go straight." And then there was a sign, you know, on the cartoon. There was a sign, you know, this typical sign with a chain, and the one chain broken, and the sign hanging skew, and it's written Judo Junction on there. So as of that day, that junction was called Judo Junction. You know, of course, whenever, suppose you had to go to Cape Town for official business, you would just take the car from the transport park the night before, overnight at your home with the car, and then drive to Cape Town. Otherwise, you have to come back in and then go back again to Bredasdorp and then to Cape Town. So in any case, and similarly, when you came back, you know, from Cape Town, you know, just kept it at your house, and next morning you drove into work. So one of the mechanics one day, he brought a Unimark from Cape Town, and surprisingly, he was called Spanner, you know. So the next morning, Spanner is driving into work, and his wife is sitting next to him, Tessa. But Unimark is a left-hand drive vehicle, so he's sitting on the left-hand drive. You know, and now, you know, if you want to overtake, you have to go. You're far out into the lane, the right-hand lane, the oncoming traffic, for him to see if there's a car. And there was the Sergeant Major driving behind him, and the Sergeant Major got very, very irritated with this guy, that he's driving all across the road, you know. So it happened, the Sergeant Major overtook them, and when they got to the gate at Tfdc, the Sergeant Major was in front of them, and the Unimark rolls up. And the Sergeant Major gets out and walks up to the Unimark, very upset, and to Tessa, and said, "Can't you drive properly?" No, and where did you get your license? I don't know what else. And Tessa said, he said, Sergeant Major, I don't even have a steering wheel, you know. So we had a lot of these funny incidences. And another one, we went, there was a dentist, and we went, he invited us to come to his farm in Wellington and do mountain flying there. So the night we camped out on his farm, you know, so some slept in the helicopter, some other in the tent or wherever. And there were these two guys, I won't mention names, exact names, but so they were groot drunk buddies, you know, so and they were very jovial and nice guys, very nice guys. And the next morning, we you know, the camp starts getting, you know, people waking up, and suddenly you hear this thundering voice over the across the yard. Van Rooyen, jou bliksem, you know, you bastard, you know. What happened? So what happened was, this guy shouting, when he went to bed, he hung up his trousers. So Van Rooyen came and he took a grease gun and pumped the legs of his trousers full of grease. so we had good fun, you know, like that time, you know. So in any case, so Chris, that was basically then, you know, about the weapon packages that, you know, with the Gripens and all those aircraft, and the Navy also got the new ships and submarines. And so one of the project was Project Flange. That was the replacement of the helicopter, the Alouette helicopter. So they went and looked at different helicopters. I'm not quite sure what and when and where, but eventually it was decided to procure the Augusta A109 LEH, the light utility helicopter. So from Tfdc side, myself and James O'Connell, the test pilot, we were called up to go to Arms Corps to negotiate the technical specification for the helicopter, because there was a user requirement specification, and so this had to be decomposed into design requirements, the technical specification. So we had a few rounds of negotiation. There was also on the Air Force side, electronic engineer Johan Maria involved in that, and then there were Arms Corps guys. The main guy was Walter Schroeder and Willem van der Westhuizen. Walter was electronic engineer, and Willem was the software guy. So we went a few times there. We also negotiated the test and evaluation master plan, you know, all the testing that had to be done on the project. And then the contract was signed. These documents became obviously the annex to the contracts. And then they decided to place a project team in Italy, at Cascina Costa, near the Malpensa airport. So there was Arms Corps members and Air Force members there. The Armed Corps side was the program manager, and then assistant program managers also worked on the engineering side. And then Air Force side, the project officer was the Lieutenant Colonel Kevin Viljoen. He was a helicopter pilot. And then the deputy project officer was at that time Lieutenant Colonel Zyxen Smang. He later became the chief of the Air Force, and I think he retired about 2 years ago. The technical officer was Lieutenant Colonel Andries Vandenberg, and his deputy was Major Wellington Kalipa at that time. And then James was appointed as the test pilot, but he only came a year later when the test flying started picking up. And I was appointed as the system and the flight test engineer. So we went to Italy, but wife and children went along. My sons were in the European school, so the older son had to do his school in Dutch, first language, and my other son also did German. So the function, especially from my side as a system engineer, was working with Augusta on the development on the one hand, and I'll get more into details now. On the other hand, we had to report back with all our, results to the Military Airworthiness Board, the MAB in South Africa. And that was it was coordinated by the Director of System Integrity. It was the Colonel Hannes Prinsloo, and one of his guys, engineers, Johan Creer, they worked on that. And then on this board, you had representation from various functions. From the ops guys, like General Hugh Payne was the director of helicopter, I think it was director of helicopter operations. and his senior staff officers. You had people from engineering, you had people from the logistics, the technical office community, you know, so it was a well represented board. So we would go back and report to them, you know, about the findings, because eventually they had to give approval to for release to service of the aircraft. So we started we had also milestones, you know, which is typical of engineering. It's the preliminary design review, critical design review. Now the first milestone was PDR. So we were working towards decomposing the aircraft level specification into the lower level specification. Just to give you an example, one of them, the displays and the avionics, the man-machine interface specification was 800 pages, because it defines every little line and detail. What's the color? What's the width of the line of the display? If there's an arc, and when does this color change to that? And and we reviewed every single page of that 800 document, just to give you an example. And they, for every system, we'll give you each one we reviewed. Now, I just need to mention, we also had a team back home. There was a JPO, Joint Aero Acquisitions Project Office or something like that. And so the Gripen and the Hawk and us, that people, you know, our project was also people working there for us. On Project Flange, there was a Major Duncan McCagney, a helicopter pilot. He was the training officer responsible for all the training on the project. And who pops up to the other guy? Sergeant Major Olivier, so very experienced in project. Then we also, and there was also like Lieutenant Colonel Malcolm Christie, a technical officer. And then we had a MMI work group, which was a group of pilots from the squadron. So for example, you know, anything to do with the design where their inputs are required, like this man-machine interface, you know, because they came as part of the review. Now, one of the members on there was Major Hutton, helicopter pilot, and he was mentioned, I think it was General Bowman or somebody mentioned about him. And he was, while we were on the project, he was tragically killed in an accident in Air Force Base Waterkloof. It was in the dark. There was a deck park, and I think with his motorbike he rode into the horizontal stabler. But what a fantastic person, really nice. So we had all of these. So support also from back home. So we would. So then we got into the next phase, was all the analysis. You know, for example, the flight controls, you had to do the analysis for the limit load, and then you also have to look at cases if the pilot pushes forward on the control stick, the other pilot pulls aft. You know, it's opposing loads, and you must calculate that. Also, there's various cases we had to do, and then we got into the what we call the qualification testing. So one of the examples is the landing gear, the strut, the oleo strut. So you do all the environmental testing. Like I say, there's a document called DO 160, which gives us specific guidelines, and there's 26 aspects you can test, you know, like altitude, vibration, temperature, all those things. Now, one of the tests that was done in Rome is the sand and dust test. And there's a specific size of the sand and the dust, because dust it goes into places you won't believe. So you have to, first you do a functional test of the oleo, and then you spray it with the sand and also with the dust. There's a specific velocity, and you have to spray all the phases. I think it's 3 hours in each. So there's a time you also spray each phase. Then after that, you do a functional check to see if this didn't impede it, and you also take it apart to see if anything got inside. So that was one qualification test. The other one of interest was also the landing gear was the drop test. So the full landing gear with a wheel, it was mounted on 2 slides, vertical slides, and you put a load on top to represent the load it would see on the aircraft, and then you drop it. You had instrumentation, you know, like accelerometers and load cells, and then you dropped it. So this is the maximum load. and see also the oleo mustn't leak. Now, you had to also consider various cases, because one case is that a helicopter comes in and lands vertically, but the other one, it does a roll-on landing. So what you did there, then we had a block, a wedge, and so the landing gear is dropped onto this wedge, and it gives the forward velocity. You also had to give sideways, so that was all of these tests that was done. Another interesting one also was maybe I should just first mention, I forgot to mention that the helicopter was basically a new helicopter to meet the Air Force requirements. And I think at the same time, it was also a good opportunity for Augusta to upgrade their helicopters, because the previous one was the 109K, ours was the 109 LUH for light utility helicopter. And then from that one, they made another one, the LUH-S, which I think they sell to Sweden. It's the Super LUH, I think was the name. So it had a new engine, new landing gear, new avionics, new fuel system. They had to change the structure for crashworthiness, because the seat was made crashworthy. So when it in a crash, it deflects. This floor had to be lowered so it doesn't hit the floor. Things like that. There was mission equipment. So it's essentially a new helicopter. But the one interesting test with the fuel system, because it's a bladder and it's inside as a structure. Just if you sit in the helicopter, just behind the aft seat in the cabin. So they took a part of the helicopter structure with a tank inside, with a tank fold up, and it's placed on a platform 50 feet up in the air, and then this platform is dropped. So for crash, and then it mustn't leak. So we did the qualification test like that. There's a certification requirements that the main rotor gearbox must be able to operate dry with no oil for 30 minutes. So because of the increased rating of this, with a higher, more powerful engine, that test was also done. Witnesses, it's quite interesting to see all the smoke coming out, and it's still operating. And then there was various ground testing. And then we got into flight testing. Some of the interesting one is the flotation gear. So it's got this flotation gear, and if it lands, emergency landing in the water, these balloons, if you like, pop out. So obviously you want to see in-flight deployment, and you actually and check the handling, because there's a transient on the aircraft, so you do the handling. We did that testing. Some photos I'll send you. Now, an interesting thing is at Augusta, there was a naval architect working there, and he was concerned with the design of the hull, for when it's in the water. And then one of the tests was conducted at near Venice. There's a excuse me, a water tunnel. Now it's like a big swimming pool. The wall, the sides are about 1.5 meters high. It's about 3 meters wide, maybe a little bit more, and about 50 meters long. And then over it is a crane, and over this is a crane, and then the crane, on that hangs the model of the helicopter. And then they create waves in this swimming pool, if you like, this tank, and you got different sea states, so you can create the waves to the different sea state. And when it's at the correct sea state, they drop this helicopter, and they see it's how when it lands in the water, it doesn't topple over or whatever the case might be. Very interesting. So flight testing, we did flight testing. The flotation gear. Another one, we did load survey. So that's where you had strain gauges all over the aircraft, including on the rotor blades, the main and tail rotor blades. And you did various maneuvers and various conditions that you tested to define the loads, including, like, for example, cargo slinging. If you've got cargo sling on there, so various conditions. So that was actually done in Kiruna, just across the border in Switzerland. And we also looked at failure cases, because the main rotor, when the pilot moves the control, it's got actuators which moves the main rotor, and each actuator's got what they say 2 bodies, 2 pistons, separate ones, and it's fed by hydraulic fluid. But each one is fed by separate hydraulic systems. So if one fails, so we did failures where you find one hydraulic system and see how the aircraft responds. So of course, there's a saying that says there's a time to come and a time to go, and now the time has come for me to go. And that's what happened to me in my last year. I realized my time in the Air Force was coming to an end. So I was really had a good career. The Air Force was good to me. It was really a good time in the Air Force. But like I say, in English, I had my innings, and so I started looking around for work, and just tested the water, apply a few times. So we were scheduled to return on the end of January 2005, and so on the 2nd of January they came to pack the moving company to pack our furniture and load it. And in this mess, I was on the phone with Pilatus Aircraft, and they said I can come for an interview. So we moved in an apartment, to return at the end of January. Our furniture is now gone to South Africa. So I went for the interview and heard nothing of them. And then on near the end of January, one Friday, the project said, can I just stay 2 weeks longer? So, meaning returning the mid of February to South Africa. And so I signed the documents, and that afternoon I get a call from Pilatus, do I want to come and work for them? Do I want a job? So I said, yes, sure. So I got a job there as a mechanical system engineer, initially on the trainer aircraft, the PC-7, PC-7 Mark II, and the PC-9. But then when I got this job, chaos erupted, because my son, with all this move, he was in matric, my older son, and he was doing homeschooling through the Cambridge University. I was busy studying for my master's degree in mechanical engineering, and so chaos erupted. So we moved back to South Africa. I resigned. I had to work 3 months' notice. We moved back to Bredasdorp, unpacked and sorted out. And in Switzerland, the places are small, so we had to sort out furniture and everything. So the end of April, they came to load our furniture again, I think it was 2 months later. So after 21 years, I left the Air Force at the end of April, and I started working at Pilatus in beginning of May. The funny part to this is where we lived in Italy on the project versus in Switzerland, in Buren, going up to Engelberg. It was 200 kilometers apart, but our furniture traveled 20,000 kilometers to come back. And so, and of course, that was the end of my Air Force career.
I have a few questions here, and it seems to me that the Air Force is very, very technical, and it seems to be very, very thorough. But there are inherent risks to the Air Force as well, because these aircraft do fly combat, they do fly at the edge. Is it possible to simulate these things like wing spotter and so in a simulator? In other words, not to go up and actually do it in the air, or do you have to go into the air at some stage?
Of course, there's 2 parts to your question. The one, if we talk about development, you do have simulator engineering simulators, that helps you, but eventually it's still the analysis and the testing that's required, so it's a means. Now, if you go into the civil certification environment, and also even in military, you have various means of showing compliance, there can be analysis, and one of them is simulation. But if you want to use that for credit, your simulator must be representative of the aircraft. So, and in a developmental cycle, that's very expensive, so you can use it as a tool for example, test pilots, the first time before they fly a new aircraft, they've got some form of simulation, and they train on that. So that's in the developmental world. In the operational world, you know, like for example, at Langebaanweg, and they had a simulator, and you can get various degree, and like I think SAA and the guys, the operational pilot, can talk more about on that. There you've got like a certified simulator that's very representative of the aircraft, and it is used as part of that, but ultimately it is also the training, you know, or the flying. But the best, you know, on the operational side is to speak to pilots, you know, the operational pilots or airline pilots, you know, because I know at Langebaanweg on the PC-7 they had a static simulator, cockpit procedural trainer, more than a simulator, in other words, a moving base. But then SAA and airlines have got the simulator, and there's also a whole lot of regulation to have it representative of the aircraft, you know, but the actual training and all that, it's best to speak with, you know, pilots, in the operating pilots, you know.
I want to make a statement here because there's a lot of foreigners watching the show, and you're all welcome. When we say foreigners, we don't mean it badly. We just mean people who's not South African and perhaps do not have the local knowledge. But you're all welcome here. There's no such thing in the South African Air Force as a special forces pilot or a special operations pilot. As far as the Air Force is concerned, once you're trained, and you have to be able to do anything and everything. And that, of course, saves a lot of money. And it's not an Air Force which can waste machines or waste pilots or anything like that. It's small. And therefore, everybody has to do its part. Now, it fascinates me when you said that the RX helicopter had like this pole going down, and then the Special Forces member, or I suppose where anybody else may wish to rescue, can just hook himself up to this. I suppose his legs are dangling over, and then they fly away with it. Now that's clever. But I know that the Rooivalk attack helicopter has like 2 seats on its wings, where you can also put people. Now, I've never actually seen anybody sit on those wings, and I don't know if they will be able to hold on with the wind and everything like that. But it shows to me there's a lot of thinking behind this. Now, would you agree to me that perhaps through boredom, but perhaps not through boredom, is this encouraged? This outside of the box thinking in the Air Force?
Yeah, of course, you know, because I would say yes, you know, obviously within limits in terms of thinking out the box, but must still be safe. You know, you must think originally, you know, when you do that, but still make it practical, you know, and usable, you know. And the Air Force is very much a technical environment. You know, you must go and speak to. A simple example, Neil Ellis was speaking about his flight engineer, Steve Coetzee, and I just read his book, and I spoke to him also, you know, when he deployed to Antarctica, and they had a hydraulic pump failure, but they didn't have a spares. So he had to be very innovative to get a pump working, because they still within the bounds of reason and safety, but he had to think out of the box to fix this pump, because that's Antarctica, you know, and that's so that's a typical example, you know, of you know, what I'm trying to say, thinking out of the box is just not do, you know, you do it within the boundary of science, you know, of engineering and safety.
Well, we are probably going to keep this fellow on hopefully soon. I'm fascinated to hear his story as well. But now I must ask you, Laurus, what happened further? I mean, you didn't stay in Switzerland. I mean, no decent person can. If I may get a little bit of a hit into Switzerland, I don't like the place at all. You left. You don't have to tell us where you are now. We're just interested to know that at some stage you left, and now you're still in aviation.
Yeah, so Chris, when I left the Air Force, I went more into the engineering world, and you know, the design engineering world, working as a mechanical systems engineer and focusing on flight control, actuation, and hydraulic systems. But I worked all on what we call civil certification programs. You know, here and there I worked on what they call a mission. You know, you would have like a business jet, and it's adapted in some forces for mission surveillance and things like that. But mostly I worked on programs, civil certification, and that in itself, that also is a very structured and methodical approach, because you have airworthiness regulations that you must comply to. In the Air Force, it's more a case of what the mission requires. You know, there's no regulation that because you start off what is required for the mission, where here it's given. And for example, the two main certification authorities, just to give you a bit of background, is the FAA and EASA, the European authority. And they have got what they call airworthiness regulations. So part 27, and they're very similar, the two, is for light aircraft. Sorry, part 23 is for light aircraft, and part 25 is for transport aircraft, and part 27 is for light helicopters, and 29 is for transport helicopters. And then you've got part 33 for engines and 35 for propellers. So an engine in itself must have a type certificate. So and then it's installed on an aircraft, and then the aircraft is type certified. Now, if you go into these parts, it's accessible. For example, FAA is just faa.gov. You can go and have a look there, get an idea. And you've got hundreds of requirements and paragraphs, and each one of them got sub-paragraphs, you know, and you've got various aspects for all the systems, the performance, flying quality structures, that all those things. So I worked in the civil certification. So you start off with a cert plan, a certification plan, which for each system, and which defines the regulations, and you in that you say how you're going to comply to that regulation. That becomes your contract with the certification authorities, and then you go into the development. Similar, like I mentioned, you know, you've got your PDR, preliminary design review, all these phases until you get eventually your type certificate. So then I worked in North America and Europe on various programs, aircraft. Just to mention a few of them. I worked on the D-Jet, which was Diamond Aircraft Company. It's a light jet. Also composites, all composites. And then I also worked on the Global 7000, which is a Bombardier aircraft. It's a business jet. Very interesting, because from a flight control point of view, that was a fly-by-wire system. The previous ones, the 5 and 6000, is the conventional powered system, flight control system, not a fly-by-wire. Then I also worked on the PC-24, a very nice aircraft. It can operate from unprepared strips, you know, not a tarred runway. Very nice aircraft. Then I worked also, so all this is on flight controls, actuation, and hydraulic systems, developing the aircraft to certify it, you know, for the relevant parts. And then I worked on I worked for a company where we would provide services for engineering services, you know. So usually when a company starts up, that's where we would come in and help them until they start establishing the company and hiring people. And then, you know, once they got their company running, we would go to another project. So there I worked on the Mitsubishi regional jet, which was from Mitsubishi in Japan. We supported them with engineering services. And then I worked on a very interesting project. It was Aerion. It's a supersonic business jet. And then the other one that was also interesting is the Alice all-electrical aircraft. Now, unfortunately, after we left, when COVID came, the Aerion, the project was cancelled. You know, they stopped the Aerion one. But the Ovid, sorry, not the Ovid, the aviation is an all-electrical aircraft. You know, because now the electrical aircrafts are coming more into. You know, there's something like 157 companies that's building electrical aircraft in some format. or other. So I worked on the Alice, and then, you know, once they got the company, so they're getting ready to do the first flight, you know, and they also, the development is very similar to what I described previously, you know. Just to give you something interesting, you know, if you look at the flaps, you know, those things that extend as you're coming to land, for that, you have to look at all the failure cases, you know. So one of the failure cases you look at is what they call asymmetrical flaps. So if flaps on the one side of the wing deploys and the other one does not, because that can cause some problems. So you have to do testing. You do analysis and modeling, and then you have to do testing. And then the other one is a flap skew, because each flap surface has got two actuators. So if they are moving the flap and one fails and only one moves, it's skew. So that can cause structural problems, or it can cause handling problems. So you got a rig that you, obviously you cannot flight test that because it's unsafe. So what you have is a what we call a rig, and it's got the actual wing with the flaps, with the tracks that it runs on, the rollers, and then the actual actuating system. And then you've got a disconnect in, for example, the shaft between the left and the right. So then you operate it, it moves, and then it's got this fixture that applies as loads on the flap itself to simulate the aerodynamic load. So it's a very complex setup and expensive, obviously. So then you would with this extend the flap and then disconnect, and you've got a disconnect mechanism while it's running, and you see how it behaves, you know. So your system must detect it, pick it up, stop it in time before there's a structural you know, it breaks off or whatever. So those are examples, very thorough to do that. Now obviously in a commercial world, you know, money also talks, you know, but the authorities, they are pretty strict on when you deal with certification. So that's after my careers, and I'm still working in the aerospace industry. And then also at times I also did was an instructor at the International Test Pilot School, where I lecturing on flying qualities, performance, flight control systems, and other topics like system engineering requirements and things like that. And speaking of about requirements, Chris, that's a very methodical, because you start off with design requirements at the aircraft level, then you break it down into the lowest form, and then you must show how you show compliance to each one. And to give you an example, on the flap system, we talk about aircraft level, system level, equipment and component level. And on a flap system, the one case I worked, there was something like nearly 700 requirements, design requirements, just at the system level. That's decomposed because in the flap system, you have all your components like the power drive unit, the actuators, the drive shafts and things like that. Each one of them has got their spec again. So it's a big hierarchy of requirements. If you go into the avionics world, that's even more, you know, like I said, that MMI document pages was 800 pages, you know, so it's a lot of work to certify the aircraft, and the problem also with certifying aircraft, from the time you apply, you've got a given time period, because these regulations have amendments. If you don't certify in that time and a new amendment comes out, you must comply to that amendment, which means change. It could mean a change because you must make now a design change, which is expensive. So the timing of the companies, you know, so usually they start until they're comfortable and the design is mature, and then they apply for certification, and then they go through the certification process. But now on the other hand, you cannot take very long to get to the mature point. So it's always a balancing act.
But isn't that dangerous? I was just thinking by myself, I mean, my field in law, what we often do is we simplify things. In other words, a client comes to you, it's normally got some story which no one's going to believe. But it doesn't matter. And then you simplify it down to a level where he actually understands the law, because no one else does. I mean, it's not for sane people. Now, are you not making it too difficult? I mean, after all, people have been flying for 120 years about now. It's the same principle, isn't it? A flap is a flap. Why is there all this requirements?
Well, firstly, you need to have a requirement to regulate it, i.e. to make it safe, so you need to have a criteria, otherwise people are just going to do stuff. Now, sure, the technology and engineering, I mean, the fundamentals don't change, but, when you deal with a specific design, it has its own challenges when you apply the fundamentals, so you have to go through all those steps. Another example is one of the certification criteria is you must consider a failure. If you've got a 4-engine aircraft, you must consider a case where all 4 engines fail, because you can fly through volcanic ash and you lose all of your engines. So you still have those requirements that you need to. And generally the difference between commercial aircraft and military can accept more risk by the nature of their business. I'm not saying they're unsafe and just gun-ho, but in the military, you're carrying paying passengers. So safety is of utmost importance, so there's a difference between that also. So, and coming back to the point, like, for example, volcanic ash, you have to show that on any aircraft, and each design has its own uniqueness. Although you've got the same criteria you must adhere to, you've got the same fundamentals you're applying, but each one it's got its own quirks and uniqueness, like all human beings also. So in that case, for example, what you have to do on every aircraft, the volcanic ash, you have to show that with all engines failed, you can what we call continue safe flight and landing. So if you take like a hydraulic system, the pump is on the engine. It's an engine-driven pump. And then you've also got electrically powered pumps. So you must show when this engine fails, you've got what they call a ram air turbine, extends, and then it provides enough power to power your essentials to get back continued safe flight and landing. And again, in that example, your hydraulic pump, the engine is stopped, so you've got no power from that. So now you must have enough electrical power to drive your electrical motor, which drive your hydraulic pumps, which provides power to your flight controls, because you must fly the aircraft. So any aircraft, you must show that it works, because there's also the dynamics. If you think about it, your engine winds down. So there's a point that you're going to start losing hydraulic power. And then the rad deploys, and then it starts winding up. So that transient period also is important, and it can vary from design to design. I'm not saying it's a big difference, but you must make sure it works, But just as a side note, on that, what you do, you've got what we call a bypass valve on the pump. So you don't actually shut the engines down when you do the hydraulic test for all the failure. You just, the pump bypasses the fluid. So there's no power hydraulic fluid, so it's only electrical pump. So you have means of conducting the test safe, with special equipment that you install on the aircraft. And that's why a development of the aircraft is very expensive. And then the other thing on top of that, just to add one more, is what we call the safety analysis. Because, if you take an aircraft and a combine harvester, the complexity is most probably the same. But if the combine harvester stops, it stops. If the aircraft stops, it falls. So we have this safety analysis, and that, if you compare the costs to each other, the engineering costs are most probably, this one is double, and because of the safety analysis. And that's again a process on its own, because you must define the functions. You do these, what they call fault tree analysis, to see what's the probability of the failure, analyzing the system. So that is the very expensive part. On top of your usual engineering is also expensive, but you've got this additional safety analysis that takes a lot of time and money.
Well, I think if people call that redundancy, and I must say, having listened to you for a few hours now, I feel quite good about flying. I take for granted there's a lot of thinking behind it, and that the aircraft is being made as safe as possible. Yes, I know people will say there's shortcuts and there's pressure on the engineers. And yeah, we've seen with Boeing, 737, they had a problem. Don't want to go into that. There's legalities there which can get us into trouble. But should someone has been listening here, Laurus, and he thought he's thinking to himself, or she's thinking to herself, man, this is exciting. I want to become a flight engineer or a flight test engineer, a mechanical engineer. What advice do you have?
Well, first thing, I just want to give a warning. Like I said earlier, you know, to work in aerospace, you don't have to be crazy, but it sure helps a lot. But but most important, it's like any engineering, it's hard work. You know, it's long hours. You know, I always tell people, what are you doing? What work? What do you do? You know, I say I do as little as possible for as long as possible for as much money as possible. But unfortunately, the only one I get right is for only as long as possible, because it's long hours. It's very tedious, you know, and you must be prepared to work hard. That's the first thing. Obviously, you must have an interest in that, and then you must. What's very important is fundamentals. You know, because if your foundation is wobbly, if you haven't got fundamentals, your foundation is wobbly. Like I said, you might get lucky for a while, but it's not sustainable. So that's important, but you must be prepared to work very hard. You know, even if you go to universities, you don't see a lot of engineering students playing rugby because it's a tough course. You work very hard. You know, I remember one of my classmates, he told me his sister studied some or other degree, and her first class was on Tuesday morning, 9 o'clock. By that time, you know, we've done a lot. So it's a lot of hard work. That's focus on the fundamentals, because, you know, it's always, I have had many cases where fundamentals saved my life, my butt, you know, because if you do that, you can't go wrong. You'll get a lot of problems. You know, I had a case where in one of the designs, they went ahead and designed changed this design, and then they came to me and said, is this okay, because this is your function? I said, well, let me check. I did an analysis and I saw, no, this doesn't work, you know. And they said, yeah, but remember, we've bought all this parts that we already ordered and everything. So I said, well, I'll go and do flight testing just to make sure. Came back, and the equipment they bought, the parts were not appropriate, so they had to change it, you know. So again, fundamentals, you know, it's very important, because if you don't follow this fundamentals in the aerospace, you can kill people, you know. Aircraft can fall, and this is also the other thing that's very important. You know, when you're busy with a design or developing an aircraft, you must always think what could go wrong, you know, because you must cover all that possibilities and see how you can negate those risks.
I was very tempted to interrupt you and to tell you that engineering students are nerds. That's why they're not on the rugby field. They might die. I'm just joking.
Yeah, they are, but not as bad as the software guys. Those are real nerds.
Well, Internet, we came to the end of probably the most fascinating episodes which I've had here. Laurus, I want to thank you. I want to thank you for your service. I want to thank you for your knowledge. You know, a lot of people don't realize what happens behind the pilot. You know, everybody just looks at the pilot, you know, it's like the Tom Cruise, the Top Gun, it's like the man. But behind him, there's the entire team, and I think you've highlighted that for us now. So I thank you for that. For the rest of you, you know what I'm going to say now. You're not unimportant. Come and talk to me. Tell me your story. You don't need to have been in special forces or one of the elite infantry battalions or to monitor a warship or anything like that. Everybody contributed to the best of his abilities or her abilities. So come and talk to me, and until we meet again, God bless.